So let's look at this term. First of all, I have two dots here, partial velocity with respect to velocity. Like I said, always I can just remove these guys. It's partial position with respect to position. And I claim, and there is a very simple derivation, like the one we used before to prove this identity, that says that d by dt for this guy is simply partial the velocity with respect to the position. Simple. You can just show it in a couple of minutes in the basic definition of R as a function of Q. If you want, you can come to my office. I just don't want to waste time with it. So please look at this now. Velocity dotted with partial velocity with respect to something. And we have mass outside. What's this?
Half of v squared.
This is V multiplied by partial V partial Q. What's that? We just did something similar. It was also V times partial V partial Q dot. This was partial T partial Q dot. The only difference is that we're just differentiating with respect to Q, not Q dot. So this term, this whole term is partial T, partial Q, only Q, not Q dot. And now we're done. So, what is term 2? Term 2 now is summation negative AIs. Let's look at the AIs first, sorry, just to convince you. Here is the AIs. This is what we found, is that this left-hand side is two terms. The first is partial T, partial Q J dot between limits minus integration of partial T, partial QJ. So if you differentiate with respect to time, you get the A again as d by dt partial T, partial QJ dot minus partial T, partial QJ. This is our A, which is the second term. The second term is simply summing all the A's. So we're summing all the T's, we have the total kinetic energy. So finally, the principle of virtual work, we have two terms. The first term was simply Qj, right? This was the first term. The second term was negative d by dt partial T partial Qj dot kinetic energy total minus partial T, partial Qj, kinetic energy total. This is equal 0, right? So simply, if it's equal 0, I'm going to just do like this. I'm going to move it to the other side. And this is the Lagrange equation. For all J. Where if you have your all non-conservative or all conservative forces, this is simply negative partial V, partial little QG. Okay? This is the magic blue equation. So, might not be a good idea, but just to show you the efficacy of this, we have 3 minutes left. I claim we can solve this problem in 3 minutes using this equation. We have enough. All what I wanted from before is just the velocity. Luckily, there's no acceleration now. Now on, we'll not generate any accelerations. It's simply all what I need from you, please, is your kinetic energy. Just give me your kinetic energy only in terms of your kinetic energy, I will write down all the equations of motion. Okay? Yes, please.
This is the kinetic energy of the entire system?
The entire system, 1/2 mv squared for each particle, and that's it. So I don't need acceleration, just you need the velocity. 1/2 mv squared. Here is the velocity. So the kinetic energy, I'm going to write it here for our example. This is our example. Simply 1/2 mass 1 times velocity squared of the first mass. It's x dot squared. Plus 1/2 mass 2 times velocity squared of the second mass. Please do it carefully. It's the I component squared plus the J component squared. Okay? So if you do this, you get x dot squared plus L squared theta dot squared. It's just only one line. L theta dot squared plus 2 x dot L cosine theta theta dot. This is your kinetic energy of the entire system. And from this scalar function, I will derive all the equations of motion using only this equation. You don't need to know anything else. Luckily, our forces here are conservative forces. So the potential energy simply is 1/2 kx squared for the spring and negative mg times the y position for the second mass, right? The y position is negative L cosine. Okay? So actually, I don't need anything from this. You don't need to know the technical details of the problem or whatever. Just give me kinetic and potential, I'm done. I'm done. Here it is. It's the x equation directly, and the theta equation directly. Okay? Just bear with me for a minute. I'll give you some time to write. So here it is. For the x equation, it's d by dt, partial t, partial u, x dot, minus partial t, partial x, equal to minus partial v, partial u coordinate, which is x. I'm writing the x equation, right? So let's do it. This is d by dt, partial t, partial x dot. Please go and differentiate this with respect to x dot. 1/2 m x dot squared, so this is 2x dot, right? So I have m1 and also m2 actually, x dot. I also have this term in x dot. Differentiate with respect to x dot, it goes away. And you have m2 L cosine theta theta dot. Minus, please bear with me for a minute. Partial t, partial x. There is no x in the t expression, because this is 0. Equals negative partial v, partial x. Here is v. I have x here, just differentiate it to get